Welcome to Week 8, Lecture 2 of EBME401. Today we're going to talk about how we can apply filters to the signals that we sampled. We've talked about sampling earlier this week, but now we want to figure out how we can filter these sampled signals. What we've talked about in the previous weeks are analog filters. These are filters that are applied to our continuous time signals in hardware using electronic components. However, we may also want to apply a filter to our signal after we've sampled it, and these filters are known as digital filters. So an overall system is generally made up of both analog filters and digital filters. They're typically both used in conjunction with one another in order to perform different types of filtering of our signals. However, the goal of both kinds of filters is the same. We want to extract desired information and suppress any unwanted information. So we can describe our digital filters much as we described our analog filters. So if you recall from our analog filters, we had an output signal, y of t, which is continuous, and this is just equal to the convolution of the impulse response of our analog filter convolved with our input signal, f of t. All right, so we're going to have the same sort of formulation now for our digital filters, just everything is going to be discrete. So here we have our discrete input, which we've written as x of n, where n is in these square brackets to represent the fact that x is discrete. We have now a discrete impulse response. So this impulse response is made up of values, which we're going to convolve with our input signal. And the output then is also going to be a discrete signal, right? And if we write this convolution here in its explicit format here with the sum, we can better understand exactly how we're combining our inputs to get an output. So we simply taking a value of our input, multiplying it by some value which is in our impulse response, and doing that for all values of our input and our impulse response, summing them all up. And when we add them together, we get the value of our output. And we'll look at that in a little bit of a more concrete example on the next slide. All right, so we can describe the impulse response of our digital filter using a series of coefficients, right? All we're doing here is multiplying these coefficients times our input signal and adding up the results to get our output signal. So for n equals 2 here in our summation over here, the filter order will be 2, and we'll have 3 total coefficients as part of our impulse response for the digital filter. Let's take a look at a graphical representation of a second-order digital filter. So the first thing that we're going to do is define the filter coefficients in our digital filter. All right, so we have h of 0, h of 1, and h of 2 that we need to define in the second-order filter. All right, so let's let the first element of h be b0, the second coefficient will be b1, and this third coefficient will be b2. All right, so now we know all of our filter coefficients. So let's start inputting our discrete data points into this digital filter. So the first data point we input is x0. So we'll take x0 and we're going to input it into our filter. And if we look at the convolution, by definition, we're going to multiply this first data point by this last element in our filter. All right, so we'll have x0 times b2. Right, then the second data point comes in as an input, and we multiply x1 times the second filter coefficient, b1. Right, this is our third data point that comes in as our input, and so we'll have x2 times b0. And then we'll sum up all of these terms, and that will be the first element of our output, y0. The first thing that we notice is that we need these 3 input points before we can generate one output point here, y0. And so again, the first element of our output will only come after we've put in 3 values of input. And so this digital filter is going to introduce a time delay, where this time delay here is 3 input points before our first output. So you could say the time delay is how long it takes us to collect these 2 additional input points that we have to put in before we can get an output. So we also notice that this delay is going to increase depending on the order of our filter. So if our filter order is 5, so we have 6 coefficients, then we'll have to put in 6 input values before 1 output value comes out. All right, so once we have our first output value, we would then do the same thing for the next set of 3 inputs in order to get the next output. So our next input value is going to be x3. All right, so what we'll do is take our x1 and we'll multiply it by b2. So we'll have x1 times b2. We then will take our input value x2 and multiply it by b1. So we'll have x2 times b1. And then we'll take this third input value here, x3, and we'll have x3 times b0. And we'll add up all of these terms here in order to get y1. All right, again, though, we had to wait for x3 to be collected before we could calculate this y1 output. So again, we have the same delay, but there is a delay that is associated with using this digital filter. Just like analog filters, we can also describe our digital filters in the frequency domain. So before, when we looked at analog filters, we converted both the input and the output sides into the frequency domain using the Fourier transform. Now, with our digital filters, we have sampled signals, and so we have to use the discrete Fourier transform. But besides that, the formulation is very similar. So if we're looking at the frequency domain, we see that we have here the frequency domain of our input signal. Here we have the discrete Fourier transform of our impulse response. So here, capital H of f is simply the DFT of our impulse response of this digital filter. And if we multiply these two, then we get our outputs, again in the frequency domain. So when we looked at analog filters, all of our frequency domain discussions were to help us understand how the analog filter affected the frequency domain. So to see how these different frequencies were changed by applying a particular filter. However, we can actually apply digital filters in the frequency domain if we're able to compute the DFT of our sampled signal. So remember, we have to actually collect all of our signal before we can calculate the DFT. But if we've collected all of our signal, we can perform a DFT and then actually apply our filters in the frequency domain. And so again, this is a big difference between our digital and our analog filters, where we can actually go into the frequency domain and perform manipulations on the spectrum of our sampled signal, where we couldn't do that when we were talking about all of these filters that we had in hardware. However, because we have to collect all of our sampled time domain signal before we can calculate the DFT, we can't use this frequency domain filter application for real-time outputs. However, looking at how our frequencies are affected by applying a digital filter can be very instructive for understanding the nature of these digital filters. Moreover, it's sometimes easier to think about applying a digital filter in the frequency domain than it is in the time domain, which is what we have to do for our analog filters. So when we talk about digital filters, there are two primary types. The first is the type of filter that we've already looked at. This is a filter which takes all of the inputs from an input signal, multiplies them by some coefficients which describe the digital filter, and adds up all the results to give us our output. So here, our output only relies on the values of the input function, this x here. And so we call these filters finite impulse response filters, partly because this impulse response here it can be described with a finite number of coefficients. There's also a second kind of digital filter where we not only multiply our input function by some coefficients, but we also take some previous outputs and multiply them by coefficients, and take the sum of the coefficients in the inputs and the sum of the coefficients of these previous outputs and combine them to get the next output here. All right, so this is really interesting because we're not only taking digital input signals and using them to calculate our output, but we're also taking these previous outputs and using them to calculate the next sort of outputs. And we call these filters infinite impulse response filters because here we no longer have these set values of coefficients that we're combining with our inputs to give us our outputs. We actually have some combination of coefficients on inputs and outputs combining together to give us our outputs. So let's first take a look at these finite impulse response, or FIR filters. So as we saw in the previous slide, the outputs depend only on delayed inputs. So these filters are known as feed-forward or non-recursive filters. And again, we see this equation down here where we only have to worry about multiplying our inputs with these coefficients to get our outputs. So FIR filters have a lot of advantages. Because they're non-recursive, they're very stable. They're also really easy to implement. We can just use the graphical representation that we saw a couple of slides ago. We take different discrete input points, multiply them by coefficients, sum them all together, and that's the value of our output. These non-recursive filters also have smooth phase properties. Here we don't have to worry about strange things happening to the phase in our frequency spectrum, which can cause some interesting problems. We only have here a uniform time delay for all of our outputs. However, FIR filters can have some disadvantages. So just like our analog filters, we want our digital filters to have a pass band and a stop band and a pretty sharp transition band. However, to get our filters to have this kind of response, we may need a lot of coefficients or a very high filter order for our FIR filters. And a high filter order means that there's a long delay between our inputs and our outputs. So we have to wait a long time from when we put in our inputs to when we actually get an output value. Infinite impulse response filters, again, depend on both the inputs and the previous output in order to calculate subsequent outputs. And so these IIR filters are often known as feedback or recursive filters. And so again, we have here our inputs, which we're multiplying by some coefficients. We have some previous outputs, which we're also multiplying by some coefficients, and using this combination to calculate these future outputs. So IIR filters do have some advantages when compared to FIR filters. In general, they require fewer coefficients than FIR filters to get a desired response. So, where we had a very high order filter for our FIR filters, in order to get this very sharp transition band, we may not need such a high order of these IIR filters in order to get the same response. This also means that they can be cheaper or faster to implement because we don't need such a high filter order. However, they do have some potential disadvantages. These filters can be unstable. So if we look at the frequency response of these filters, we can very roughly calculate this as the discrete Fourier transform of all of these coefficients to our inputs divided by the DFT of these coefficients, which we multiply our outputs by. And so this ratio could have a very strange nonlinear phase. And this is one of the major disadvantages of these IIR filters, that we have to be very careful about their properties before we start applying them to generate outputs. We also have some filters that we can't describe using our normal frequency response notation. So here we can't really calculate the DFT of these filters. So the first of this type of filter is known as an adaptive filter. So an adaptive filter is modified to adapt to the properties of our input signal. So here, instead of having some set coefficients that are part of our filter, we can change these filter coefficients. And so here, we're changing the coefficients with every time step m. And these coefficients can be chosen to minimize the error between the inputs and the desired response in some sort of iterative fashion. All right, so we can very carefully tune the way our filter reacts to certain inputs in order to give us the desired output. A second class of filter that can't be described using a frequency response are nonlinear filters. And these are filters which act upon the inputs in a nonlinear way. These filters are really interesting. They're often used in imaging, which we'll talk about in the next lecture. And there are a lot of examples of nonlinear filters in the text that comes along with this week. All right, so we've seen the difference between two different types of digital filters, but I just want to very briefly talk about the difference between analog and digital filters. So these digital filters that we've just talked about have discrete coefficients. These coefficients can be stored in memory, which often makes these filters very easy to implement. Also for higher order filters, where we have a lot of coefficients, these are pretty easy to implement in comparison to analog filters. So first of all, we have no potentially nonlinear electronic components, which we could have in our analog filters. And the coefficients can also be easily modified, so we can better control our filter. So you can imagine building a system which has a whole bunch of different electronic components, and then wanting to swap out, for instance, a capacitor or resistor. And this might be more difficult in an analog filter than it would be to just change a coefficient which is stored in memory in a digital filter. Analog filters, however, do have advantages. For instance, they can be more cost effective when we're building a very simple filter. So for the lower order filters, it might make more sense just to build something in hardware than it would be to have a separate digital filter where we have to program this filter. So analog filters typically involve less latency and also less power consumption. And an advantage that's not listed on the slide is just that some filters have to be built as analog filters. So for instance, our anti-aliasing filters are built in hardware before we sample our signal. And so these analog filters have to be analog filters so that we can avoid aliasing of high frequency signal components before we start sampling our signal and then applying subsequent digital filters. Let's take a look at an example of a digital filter. And the example that we're going to look at is a moving average, right? This is a very, very simple digital filter. So here, our filter coefficients are going to be equal to 1 over the filter order, capital N, plus 1. So for this example, let's look at a filter order 4. Right, so here, each of the coefficients are going to be equal to 1 over 4 plus 1, or 1 over 5. Okay, and we're going to have 5 separate coefficients, which go along with the 5 pieces of input that we're going to multiply by coefficients and add together in order to get our outputs. So we can write the impulse response of our filter in this way. So we see we have our coefficients here, and they're all going to be multiplied by our inputs, which are delayed by 1 sampling point at a time. All right, so we see that this is an example, again, of an FIR filter because we're only taking values of our inputs and combining them together to get an output. All right, so we can calculate the transfer function of this filter by taking the DFT of these coefficients. And this will help us understand, again, how our filter is going to change different frequency components of our input signal. Okay, so what you're seeing on the right-hand side is the frequency response for our order 5 moving average filter. So I've plotted our moving average filter in the frequency domain here from minus Fs over 2 to Fs over 2 minus F0. Okay, so we can see here, if we just draw a line at our 0 frequency, we see that low frequencies are going to be attenuated very little, right? That here we're very close to 1 for these low frequencies. Here, frequencies at minus 0.2 hertz and 0.2 hertz are going to be completely attenuated. And then these other frequencies moving forward, they may pass through a little bit, but they'll be mostly attenuated. And again, to generate this plot, I had to make some assumptions. So first I picked a T0 of 512 seconds and a TS, a sampling interval, of 1 second. And so when I was making my plot, my F0, this is my spectral resolution, is 0.002 hertz, and my sampling frequency is 1 hertz. And this is again why here I'm plotting this from minus 0.5 hertz to 0.5 hertz. Okay, so you'll see in some of the homeworks that we often plot only this portion here from 0 up to Fs over 2 because the frequency response will be symmetric. All right, so again, when we talk about filters, we often only look at half of this plot because we know what the other half is going to be. But here I'm choosing to plot both sides because I find it a little bit easier to look at later when we talk about multidimensional signals and imaging. So what we're seeing from our frequency response is that a moving average is essentially a low-pass filter. All right, we talked on the previous slide about how frequencies near 0 Hz are going to be retained, but the larger frequencies will be attenuated. We see some strange behavior a little bit, that we have a maximum attenuation for signals with frequencies at 0.2 Hz and 0.4 Hz, and here on the negative components. But again, other larger frequencies will also be attenuated. So we see here that we're multiplying a 0.3 Hz signal by a pretty large number, so we're going to suppress it for the most part. And if we think about what a moving average is doing, it makes sense that it's acting as a low-pass filter. So we know that some of our really high frequency signals will cancel each other if we're summing over 5 different values of inputs in our moving average, right? And we'll take a look at an example in a second, but just, it's important to think about exactly what our moving average is trying to do. We're trying to smooth out high frequency noise. So this is completely expected that this moving average is a low pass filter. Okay, so let's apply our moving average filter to some actual data. So I've made a signal here, f of t, which is the sum of 3 different sinusoidal signals with different frequencies. So here my f of t is sine of omega t plus sine of 10 omega t plus sine of 100 omega t. So we have this very low frequency component, a medium frequency component, and a high frequency component. All right, so if we calculate what the frequencies of each of these sinusoids are in hertz, we see that this component would correspond to 0.002 hertz, this component here to 0.02 hertz, and this component here to 0.2 hertz. Okay, so let's think back to what our filter was doing. So we're going to actually apply this filter by convolving our elements of the impulse response with our sampled input signals in order to get our outputs. All right, so let's think about what we expect our output signal to look like. Well, thinking back to the frequency response on the previous slide, we saw that frequencies that are very close to 0 will pass through this filter mostly unscathed. So this portion of our signal should pass through just fine. We should have a gain of about 1. These moderate frequency signals should also pass through pretty reasonably, right? So 0.02 hertz, that's close to 0. So we may have a little bit of attenuation for this component, but this guy should pass through as well. However, we saw that frequencies of 0.2 hertz should be completely suppressed by our moving average filter. This is a frequency where if we sum an average over 5 points, we should exactly get a cancellation for frequencies of 0.2 hertz. And so we should completely lose all of the very high frequency components of our raw signal. All right, so let's see if that is what happens when we actually apply our filter using this convolution that we have down here. All right, so we see if we take our raw signal, which is on the left-hand side, and we pass it through our moving average filter. So essentially, this is a moving average with a width of 5. We see that our filtered signal has the properties that we expect it to. So first of all, we see this very low frequency oscillation here. So this was the component at 0.002 hertz, right, that we've retained. We also see this slightly higher frequency component here, which I'm just drawing part of in red. So this is our 0.02 hertz component. We see that it might be distorted a little bit because we've attenuated it somewhat. We're not letting it pass through quite as easily as the very, very low frequency portion of the signal, but we've mostly retained it. All right, so indeed, our filter is acting as we expect. But most importantly, we have these very high frequency oscillations in our raw signal, which are completely gone from our filtered signal. So this high frequency portion at 0.2 hertz, that has been completely eliminated by our moving average filter, which is exactly what we would have predicted by looking at the frequency response of this filter in the frequency domain. All right, so here we've chosen to apply our filter in the time domain by performing a convolution. Well, we could do exactly the same thing by applying our filter in the frequency domain after performing a DFT on both our raw signal and our impulse response. So both would be equivalent, and I would encourage you to actually apply filters both in the time domain and in the frequency domain when we're looking at digital filters. So we saw on the previous slide that our moving average filter is a low-pass filter, but it's not really a very good low-pass filter. So what I've replicated in this purple line here, this is the actual frequency response of our moving average filter. Right, I'm just drawing it over again so it's easier to see. Okay, so this is capital H of K. Okay. But we know that what we want out of an ideal filter is to have a stop band, a pass band, and really a minimal transition band. So our ideal filter would look something like this here, right? There's our stop band. Here's our pass band, where we have complete transmission. And again, our stop band on the other side, where we have perfect attenuation, right? This green line was the frequency response of our ideal filter. And again, our moving average filter is kind of not so great. Like I would call basically everything in this range kind of the transition zone where we're not completely letting our signals through, but we haven't completely attenuated those signals for the most part. So we could build a better low-pass filter than the moving average filter. However, we know that if we wanted to make a filter that approximated our ideal filter a little bit better, we'd need significantly more coefficients than our moving average filter, right? We had a filter order of 4 with only 5 coefficients. This wasn't really enough to get this nice, sharp, ideal filter and the characteristics that we see in the green line. So, we know what we would have to do in order to make a better filter, but we may not choose to actually implement a filter with all of those coefficients because it would be more computationally expensive and also result in a larger delay of our output signal. And so the goal of designing a good digital filter is one that will give us this desired effect, so approximate the ideal filter as best we can while using a very small number of coefficients. So filter design is really an art in and of itself. And there's a number of different ways of doing it, but we're just going to use the built-in MATLAB functions when we design our digital filters. So you'll see in the homeworks and also for your EKG project, you'll be designing digital filters. We can design both FIR filters and IIR filters in MATLAB. So for FIR filters, we need to specify the filter type, the attenuation characteristics, so where we want signals to be, or what frequencies we want to be transmitted, what frequencies we want to be suppressed, and we also generally will specify the filter order. So when I'm designing an FIR filter, I start with a lower order filter, see how good I can make it, and then I can increase the filter if I need to. So first we use the function FIR1 in MATLAB to generate our filter, and then we can use the function FREQZ, freqz, to plot what this filter actually looks like. We can also use MATLAB to design IIR filters. And so here we use some analog filter types as a starting point for these digital IIR filters. So for instance, a Butterworth filter is a common analog filter. And so we can use this to start our design process. We also have different orders of Chebyshev filters, which we can use as a basis for our digital IIR filters. All right, so here we can use the commands BUTTORD. This will tell us the order that we need for our Butterworth filter, and then we can use the command butter in order to design our filter. And there's similar commands for different types of IIR filters. And so what we're actually doing in MATLAB is a two-step process, again, figuring out the order of the filter that we need and then actually designing the filter. There are other ways to design these IIR filters. For instance, we could use Ewell-Walker filter design, which would determine the filter order and the actual form of the filter all in one step. But I leave this up to you to decide how you want to decide your IIR filters. So again, learning how to design these filters in MATLAB and to understand their characteristics and how they're actually affecting the signal is going to be very important for your ECG project. This is basically the bulk of what you'll be doing in the signal processing portion of the ECG project. All right, so in this lecture, we've taken a look at how we can take sampled signals and filter them using digital filters. And we've also understood how we can look at digital filters both in the time domain and in the frequency domain. And so you guys will be playing with a lot of these digital filters moving forward. So I hope you have a good time doing that. Thanks a lot.